Welcome to qnawire.
Okay, so we are going to find the fraction of the neutron's kinetic energy transferred to the nucleus of a carbon atom after an elastic head-on collision. Let's start off with the equation that we need, which is comparing the two kinetic energy values that we need. We are comparing the kinetic energy of the atom to the initial kinetic energy of the neutron. So that's going to be 1/2 times the mass of the atom times the velocity of the atom squared, divided by 1/2 times the mass of the neutron multiplied by the initial velocity squared of the neutron. Now we don't know what the final velocity of the atom is going to be, but what we do know is the relationship between the atom and the neutron based on the fact that the atom is not moving when they collide. We know that V2F is equal to m over the masses of the atoms added together multiplied by the initial speed of the other object. So we can just replace that into the equation that we already have built. 1/2 m multiplied by VI, V1I, also all squared, then divided by 1/2 mV1I squared. Now what we can do is remove our common factors from this division that we have, creating a much easier mathematical problem to solve. We know the mass of the carbon nucleus is 12 times the mass of the neutron. So we'll take the mass of the neutron as 1 and the mass of the atom as 12 to make our math simple. We therefore have 12 multiplied by 2 times 1 over 1 plus 12 squared over 1. So by putting that in a calculator, you should end up with 0.284 as your ratio. Now what we're going to do is we're going to use that ratio to help us find the final kinetic energy of both objects after they collide, assuming that we know the initial kinetic energy is 1.6 times 10 to the negative 13 joules for the neutron. So kinetic energy is always conserved in an elastic collision. We know that to be true, so let's write this down. The kinetic energy initial for each object is equal to the kinetic energy final for each object. Now the kinetic energy of the atom initially is 0, so we'll just cross that out because it's going to be 0. We also already know the initial kinetic energy of the neutron. Ke1I is equal to 1.6 times 10 to the negative 13 joules. Now from our previous question, we also know that Ke2F is equal to 0.284 multiplied by Ke1 initial. So now we can find that by just substituting in and calculating. It ends up being 4.54 times 10 to the negative 14 joules, obviously, because we're working with energy. Now, because we already know two of these things, we can find the third, just by substituting into that equation above. So, 1.6 times 10 to the negative 13 is equal to the kinetic energy of my neutron, final, plus 4.54 times 10 to the negative 14. So by a simple rearrangement, we can see the kinetic energy of the neutron is going to be 1.15 times 10 to the negative 13 joules.